jet streams form as a result of that. So as the Arctic warms much faster than the equator, the jet stream slows down and it becomes much, much wavier in the north-south direction. And these waves can get stuck in place. And this is why we get the extreme weather events. To give you an example, a high pressure in the ridges of the wave, it was stuck over Greenland a lot in 2019, and therefore the skies were clear, and in the winter it didn't get much snow, so it had a record net ice loss of 532 gigatons of ice, and that's double the average loss over the last few decades. That will, of course, contribute greatly to sea level rise, and that was also usually coincide with a sea ice minimum, near a record sea ice minimum. So all of these things, but that's basically the gist of it. So because the jet stream guide storms as well, the storms are moving slower because the jet stream is moving slower. So, and also for every degree Celsius rise in temperature, there's a 7% increase in water vapor in the atmosphere. So there's more water vapor, and as the water vapor rises and condenses into droplets, it releases energy. So the energy in the atmosphere is much, much greater now than it was before. So all of these things are working to cause problems for humanity. And I see the biggest problem being, our ability to grow food.
Right, yeah. I mean, that's what a lot of people don't realize, is that there are only like half a dozen major food growing regions in the world. Two of those fail in the same Say something before I get to the personal stuff, which I want to go to now. But,
can I say one more thing about the food? I'll do a video very shortly, so this is a heads up. I've done one in the past, but basically the valley the Central Valley in California, it represents 1% of agricultural area in the U.S. And I read that it's about 25% of the food supply in the U.S. Okay, now just before the Civil War, there was something called an atmospheric river. These exist. It's like regions in the atmosphere, with very, very high amounts of moisture. And it started raining in California. This was 1862, I believe, and it didn't stop raining. And you basically had the California Valley filled with water. So Sacramento was under I don't know, 10 feet, 15 feet of water. So that whole fertile valley was covered in water. And this is not a one-of, this is a periodic event. And it's overdue. So imagine something like that, and the climate change should make it a higher probability, higher risk of occurring. So imagine that happening, knocking out a quarter of the U.S. food supply in just one, in a matter of a few months, right? Right. Well, so there's all of these black swans, if you like, these, very, very low probability events, but if climate change is making them higher probability, riskier, and, the idea of a 1 in 1,000 or 1 in 100 or whatever, those numbers assume a stable climate, and we don't have a stable climate. So those numbers are generally out to lunch.
Say something about a lot of people don't know. It was news to me when I first learned a few years ago from you and Nick Humphrey mostly, that the energy, why is it that the loss of ice, the loss of the cryosphere is such a big deal? Say something about latent heat and that sort of thing.
Right. Okay. So my last video, I talked about the overall loss of the cryosphere, and we've lost 28 trillion tons of ice on the planet in the last 23 years. 23 years. This was up to 2017. I think the study only took data up to 2017, and the study just came out last week. So in 23 years, ending in 2017, 28 trillion tons. I mean, this, and I mean, some components wouldn't raise sea level, like Arctic sea ice, but then, Greenland is high up there, and Antarctica is high up there, and, the Southern Ocean, the Northern Hemisphere is about 60% of that loss is in the Northern Hemisphere, about 40% in the Southern Hemisphere. And the energy, in order to melt all of that ice, was about 3% of the total net solar radiation hitting the Earth. So what that means is, as we have less and less ice, the ice keeps the Arctic cold, and the Arctic is cold so that there's ice, right? So it's like both things are happening. So as the Arctic warms and we get less ice, and the Arctic warms more, we get even less ice and less ice, then the Arctic, like in the summer, the air temperature right at the surface of the ocean over the ice is close to the freezing point of the ice. Now, because it's ocean water, salty, it's about minus 1.8 degrees Celsius instead of 0 degrees Celsius, the freezing point. But then as we get melt and then freeze and melt and freeze, there's less salt is rejected, but not generally that much in first year ice. Although if you take first year ice and melt it, there's going to be brine pockets in it, so you're going to get some salty water. But anyway, whatever close to the freezing point. So the atmosphere is pegged at that temperature. So without ice, then and the amount of energy, the number I give is if you've got a kilogram of ice, and you melt that kilogram of ice with a certain amount of energy, right? And now you take that energy and you apply it to the water that's slightly above freezing, right? It'll bring the water temperature up to about 70 degrees Celsius, that kilogram of water. Okay, so it takes a tremendous amount of energy to melt the ice, and that keeps so that's the latent heat, the stored component. And then when you have no ice left, then all that energy goes into heating the water, and that's the sensible heat. It's called the sensible heat. So the ice, it keeps the Arctic cold. When the ice is gone, the temperature will skyrocket. Now, if you look at the German data, the DMI data on the Arctic temperature north of 80 degrees Celsius, and I'm going to do a number of Arctic videos again very soon on this, because there's a couple of very significant papers that have just come out recently, and one of them is talking about the warm water underneath. Normally you'd have the ice, and then it would be melting, and you'd have some fresh water lens at the surface, and then underneath would be warmer water. And the reason why it was underneath is because it was heavier, because it was laden with salt. Okay, so the buoyancy of the density of ocean water depends on two things, on the temperature and on the salt content. So you can have warmer water underneath colder water, and the warmer water being denser because it's laden with salt, and that makes it heavier. So as there's enough heat underneath in that, and normally it's about 150 meters below the ice, but I'll be discussing a paper in a few days about how that's shallowing. It's no longer 80 meters, it's no longer 150 meters below. In some regions it's 80 meters, in some regions it's mixing with the surface water. There's enough energy there to melt the ice that is in the Arctic right now 4 times over. So I think this is one of the abrupt tipping point changes in the Arctic. And one of the terms is Atlantification of the Arctic. Like as you get mixing of that water, then there's already mixing on parts of the outskirts of the Arctic, and this is why the ice doesn't form there even in the winter. Okay, so I think it's pretty clear that once this process extends across the Arctic, there'll be no ice in the Arctic year-round. And then we're in a totally different situation, because the only cold spot left up in the Arctic will be Greenland. So, the jet stream, why would they circle around the North Pole? They're going to circle around the cold part, which is the center of Greenland. The center of Greenland is offset from the North Pole about 17 degrees. It's about 73 degrees latitude north. So not only are the jet streams slowing down and becoming wavier, but if they change their center of rotation, right, then, our weather patterns go to hell, basically.
Yeah, a complex civilization based on growing grain and scale.
可以呀。
Climate change.
嗯。